Hello, today I shall teach you a special class of equations which are called Bernoulli equations. This is part of section 1.6. In this section we have three different types: Bernoulli equations, homogeneous equations, and exact equations. They are all solved with special methods. For Bernoulli equations we shall use a special substitution. The equations are called this way after famous Swiss mathematician Bernoulli, who has great contributions to mathematics. There are also other Bernoulli equations in the theory of fluids. This one here has numerous applications, and you can see some of them in the book. For instance, it appears in the studying flight trajectories and other places. I want to focus here on the technical solution. So you can see here the standard form of the Bernoulli equation. It extends the linear equation. If m, the power of y on the right hand side, is 0, you have a linear equation. If m is 1, this will be a separable equation. So we exclude these cases. We solve this equation by introducing a new function, substitution in the function. And there is a very strict formal procedure how to find the solution. So first step is to divide both sides by y to power m. So we divide by y power m both sides, and the result will be, I shall write this way, y minus m y prime plus px y 1 minus m power equals qx. In this situation we look at the middle term, and the function which appears here we call a new function. New function will be vx, which is y power 1 minus m of x. And then we have to rewrite the entire equation in terms of v. The equation will become linear equation. We will solve this equation and then return to the original function y. So I want to show you now several examples. Look at this equation. Examples. So our first example will be the equation 2x y prime plus 6y equals x cubed y cubed. Well, this equation is not in standard form, so we divide by 2x both sides to bring it to the standard form. The equation becomes y prime plus, I shall write on purpose this way, 3 over x times y. So I want to separate the coefficient in front of y. And this equals x squared over 2 y cubed. So this is now a Bernoulli equation in standard form, and we start the procedure. We apply our special procedure. So here m is 3. We divide by y cubed both sides. The equation becomes y negative third y prime. Instead of writing a denominator, I prefer to write with this negative power. Then we have 3 over x y negative second power, and this equals x squared over 2. Okay, so we look at the middle term and we introduce new function vx to be y negative second of x. This is our new function. Now, we want to rewrite the entire equation in terms of v. Here in this place, in the middle term, we put v. We have to find a relation between the derivatives of v and y in order to replace y prime. So we differentiate v of x. The result will be v prime equals negative 2 y negative third power y prime by the chain rule. So we differentiate by the extended power rule. Actually, this is using together the power rule and the chain rule. And now you can see this product y negative third y second appearing here. So we write y negative third y prime, y negative y prime. This is v prime divided by negative 2. Put this in the equation. And then the equation becomes v prime over negative 2 plus 3 over x v. Now in the place of y negative second we put v. And this equals x squared over 2. This equation, written in terms of v, is a linear equation. But it's not in standard form because v prime has some denominator here. To bring it to standard form, we multiply both sides by 2. And the equation becomes v prime plus, on purpose I want to separate this coefficient, it becomes negative 6 over x times v. And this is negative x squared on the right side. We have a linear equation in standard form. Okay, we can start to solve it now. I want to emphasize that before solving a linear equation, it has to be put in standard form. Otherwise, the solution is not correct. You may get a very wrong integrating factor. Now for this equation, integrating factor will be exponential integral negative 6 over x dx, using the function here with v. And solving this integral, we have exponential negative 6, just a second, negative 6 natural log x, no absolute value, which is exponential natural log x negative 6 power, and this is x negative 6 power. Our integrating factor is x negative 6 power. And now we multiply the standard form by the integrating factor throughout. And the result will be v prime x negative 6 power. Now I'm removing the parentheses. This becomes minus 6x negative 7th power times v. And on the right side, we have negative x negative 4th power. The left-hand side in this equation is one exact derivative. Vx negative 6, all this prime, equals negative x negative 4th power. We can verify this using the product rule. After we come to this place, we integrate both sides. And when we integrate, we get Vx negative 6 equals negative x, adding 1, negative 3, divided by negative 3 plus c. Now I shall rewrite this with positive powers to make it better visible. This will be, okay, this is v over x 6 power equals 1 over 3x cubed plus c. Solving for v, so we multiply both sides by x 6 power. And then v becomes x cubed over 3 plus c x 6 power. Then we shall return to the function y. Remember that v is y negative second. So this is 1 over y squared. We need to flip both sides, but now we have to be careful how we flip. In order to flip, we need to write common denominator. So we write 1 over y squared. Common denominator is just 3, so this will be x cubed. 3 times c is again arbitrary constant c, plus cx 6 power over 3. And then we flip. Y squared is 3 on the top over x cubed plus cx 6 power. Okay, this is our general solution. If we have initial conditions, of course we can solve them. Let's suppose we have initial condition y of 1 equals 2. With this initial condition, we set x equals 1, and then y will be 2, so there will be 4 equals 3 over 1 plus c. From here, 1 plus c equals 3/4, c equals 3/4 minus 1 will be negative 1/4. And we can put this in the general solution and find our particular solution. Another example. Another Bernoulli equation. Solve this equation. Y second y prime plus 2x y cubed equals 10x. The equation is not in standard form. It's to make it standard form, we have to divide by y squared. It becomes y prime plus 2xy equals 10x y negative second. And then we see a Bernoulli equation. M is negative 2. We have to divide both sides by y negative second or multiply by y cubed, by y squared. And then we come to the original equation. Actually, there is nothing wrong. Y squared y prime plus 2x y cubed equals 10x. So we made a step back and forth, but everything is correct. Now, if we have some more experience, we can recognize that from the very beginning, we need to set v equals y cubed to be a new function, the one that stands here in the middle position. But if we don't have much experience, we have to follow the rules, and the rules say, bring it to standard form, apply the procedure. And that's what happens here. There is nothing wrong. So with this new function, we differentiate v. V prime will be 3y squared y prime. The product y squared y prime, this will be v prime divided by 3. We put this here in the first position. The new equation becomes v prime over 3 plus 2xv equals 10x. Linear, not in standard form. So we multiply by 3. The equation becomes v prime plus 6xv equals 30x. Linear equation in standard form. We continue. Here we find integrating factor, integral 6x dx. So this will be exponential 3x squared. This is our integrating factor. We multiply the standard form by this. V prime exponential 3x squared plus 6x. I shall put exponential in this position. V equals 30x exponential 3x squared. So I claim that the left-hand side is exact derivative. And it will be the derivative of V exponential 3x squared, the integrating factor. And the equation becomes this left-hand side equals 30x exponential 3x squared. Let's check here on the side, what is the derivative of exponential 3x squared? This will be 3x squared prime, which is 6x, and repeat the exponential. Okay. If we look at the equation again, the left-hand side is exactly the derivative of v times the exponential plus derivative exponential times v. By the product rule, we have exact derivative here. Okay, now we have to integrate, but before we approach integration, we notice that the right-hand side is also exact derivative. We can write the right-hand side like 5 times, okay, let's make it better, 5 times 6x exponential 3x squared, and remember, we just found that this is a derivative exponential 3x squared. And our original equation takes a very interesting form. It has the form v times exponential 3x squared all this prime equals 5 times exponential 3x squared prime. So I hope you appreciate this transformation. We're just rewriting the original equation using Bernoulli's method. I can even return to the original function right here. Replace v by, remember, v is y cubed. So let's replace it here. Y cubed exponential 3x squared all this prime equals 5 times exponential 3x squared prime. This is our original equation, written in a very special form, very convenient for integration. So integration now is quite simple. We have these functions here have equality of two derivatives, so integration just gives you y cubed exponential 3x squared equals 5 exponential 3x squared plus c. 5 we don't touch, that's just the coefficient. Look at this. Now we can solve for y cubed. For this purpose, we divide both sides by exponential 3x squared, which is the same, multiplied by the reciprocal, both sides. And we get y cubed equals 5, just 5, plus c exponential negative 3x squared. Don't forget to put it here. And this is our general solution. And we can now take cube roots here. Solve for y this way. 5 plus c exponential negative 3x squared, 1/3 power. If c is 0, we have very special solution. Y cubed equals 5, y equals 3rd root of 5. Very special solution for our equation. Okay, enough with this lecture. Please read the additional notes on Moodle, the examples there. You can watch additional videos and also read the material from the book. Goodbye.